Yeah.
Hi everyone.
Okay. Hi everyone. Welcome to today's webinar, Faster Benchmark of Architectures, Power Switches, Topologies, and Detailed Design. I'm Aurélie, and I'll be your moderator during this webinar. I work on the marketing team here at Power Design Technologies. I am proud and excited to be hosting this session today. Together with the PowerSIM team, we at Power Design Technologies have worked hard to create this webinar, and we all hope that it will help you learn more about the PowerForge PSIM Alliance and how to make the most out of the seamless integration we've created for your power converters development. I'm very pleased to introduce today's speakers, Albert Danford and Guillaume Fontes. Guillaume Fontes is our CSO and co-founder at Power Design Technologies. He's our PowerForge software expert that is co-developed and our power converter benchmark and design guru. Today, Guillaume is going to show you how to score on competitive power converter solutions by exploring and benchmarking new design options and export your best solution to PSIM for further project development. Albert is the CTO at PowerSIM, and he's presented dozens of webinars with over 350K views. He's recognized by all PSIM users as the great support he's been providing on power converter and motor drive designs. Today is going to share how to really nail your PSIM usage to generate simulations for MV drives and DC fast chargers, and highlight very valuable features and settings of the PSIM software for advised decision making. Before I hand the mic over to Albert and Guillaume, there are a couple of topics I'd like to tackle about this presentation. First, today's webinar will be available on demand after the live session and is accessible through the same link you're using now or on the Power Design Technologies page you've registered. Next, we all would love to hear from you during today's presentation. So if you have a question for our speakers, please feel free to send it through the questions tab indicated by the question mark at the right-hand side of your player. We'll be answering questions throughout the webinar. We've also scheduled a dedicated slot at the end of the session for the remaining questions. And if we don't get to your question during today's webinar, we will be sure to follow up afterward. So without any further ado, let's kick things off by welcoming my CSO, Guillaume Fontes, and Albert Danford, CTO of PowerSIM. Guillaume, Albert, over to you.
Okay, well, thanks a lot, Ollie, for this kind introduction. So, yeah, I'm very pleased to be here with Albert. Okay, to present you a design workflow from faster benchmark of power switches and topologies using PowerForge to a detailed design using PSIM. So the agenda of this webinar is the following. So first of all, I would say a few words about the complementarity between PowerForge and PSIM tools. And then we will focus on two examples. First, a medium voltage drive and a DC fast charger for electrical vehicle. Then we'll jump into conclusion, and at last, as Ollie said, we will have a special slot for live question and answers. But of course, do not hesitate to ask questions during the webinars, and we'll try to answer them. So PowerForge and PSIM offer very interesting complementarity. Okay, if we have a look at power electronics engineer workflow, indeed, okay, in the early stage design phase, the designer using PowerForge can explore different degrees of freedom and especially benchmark topologies or power switch reference and also switching frequency. Thus, to compare different design solutions and choose the best ones to export into PSIM, where he can generate waveform, check semi-conductor process, setup scripting for automated analysis, or close control loops and generate code for MCU implementation. So now I'm going to say a few words about PowerForge, and Albert will do the same about PSIM. So what's PowerForge? PowerForge is an innovative benchmark software for power converters. Yeah, the main strength of this software is that it allows the designer to benchmark different topologies from two-level and classical topologies to multi-level topologies, and also benchmark different components such as classical power switches, IGBT MOSFETs, but also silicon carbide MOSFETs. And for two conversion stages, a non-isolated DC-DC converter, and also a three-phase inverter, especially useful for voltage for variable frequency drive. It's also web-based application, so it's accessible anywhere, and it's very easy to collaborate with different users with proper access rights. About PSIM, I'll let Albert say a few words.
Yeah, thank you. Yeah, so PSIM was originally developed in the 90s. PSIM started. Our founder, Dr. Hua Jin, was a little frustrated with the existing tools for simulating power electronics that were available at that time. So the main characteristic of a power electronic simulation or topology is switching events. So hard derivatives in the voltage and current when the devices transition state. And that can cause computational issues with, or did cause and does cause computational issues with some of the traditional tools. So he started to write PSIM as a dedicated simulation tool for power electronics to with an optimal solve algorithm to deal with those large and sudden derivatives. And as a result, PSIM has now been around for about coming up on 20 years. So PSIM, the main purpose behind PSIM has always been to be fast and efficient and computationally robust. And we allow you to simulate things like losses, which you'll see today, so switching and conduction losses on the devices, closed loops with analog or digital control, devise machine and mechanical loads and circuits, allow you to have PV models or battery or wind power turbines, ideal or non-ideal switch models. So ideal switches is basically an ideal transition between on and off, and we have non-ideal switch models which actually simulate that transition given a certain gate drive circuit. And then embedded code generation for select TI C2000 MCUs, so allowing you to have a digital control algorithm with peripheral blocks defining how the PWM and the ADC will behave. And when you generate code, you literally don't have to write a single line of C code to get that code working on the MCU. We'll see that I have an example for that a bit later. Scripting allows for automation of your simulations and analysis. Again, we've got an example of how you can use some scripting a little bit later as well. This allows you to set up you've got your topology and you want to run it through some benchmarking. This is what scripting will allow you to do. You could just basically write a script and then go and have a coffee while it does the work for you. And then also we're pushing to LT Spice now. So PSIM allows you to dual define switch models and link to LT Spice. Although I would strongly discourage trying to run a Spice simulation of a multi-level inverter topology. That is definitely what Spice cannot handle. So with that, I think I'll pass back to Guillaume.
Yeah, well, thanks, Albert. Okay, so PowerForge and PSIM can be both used for a wide range of applications, such as energy storage or renewable energies, naval mining applications, and also electric vehicles. So in this webinar, we are going to focus on two examples. First, a medium voltage drive application, so such as naval, offshore wind turbines, or mining applications, and then a second example of a DC fast charger. So about the medium voltage drive application, as I said, it's used in a wide range of applications, mining, naval, and offshore wind turbines. And so in this context, a major use case is the retrofit of an existing motor originally powered straight from the grid. So in this use case, it's very interesting to introduce a variable speed drive, as it saves motor replacements, but it also increases the operating efficiency of the existing motor, and it also increases safety. But it used to be a motor originally powered straight from the grid. We need to be very careful about the motoring distress, and especially about the total, about the current distortion, the THD. So, and in such cases, using multi-level topology is very interesting. So the requirements of the drive we are going to consider of the following: phase voltage of 3.3 kilovolts, a power of a little bit more than 2 megawatts, and a frequency, AC frequency of 50 hertz. So, and we are going to apply the previously described workflow to this example of a medium voltage drive. So first, with PowerForge, we are going to benchmark different multi-level topologies and to see the influence of the THD, the current THD, but we are also going to benchmark different power switch references and see the influence on the efficiency versus specific power and also the cost. Then with PSIM, Albert will show you how to generate waveforms and check power switch losses, for example, and he will also show you an example of setup scripting for an automated analysis with a parameter variation. So let's go for the live demo, and I'm going to switch to PowerForge. Okay, so as I told you, it's a web-based application, so I just need a login and a password, so to get the proper access right. Here we are. So this is on my main page. So you can recognize here two subsections, a project subsection and a library subsection. So here you can recognize, okay, the two projects we are going to consider today, the DC fast charger and the medium voltage drive. And so here are the libraries we are considering, and especially here, okay, the power switch library to benchmark power switches. So to give you an example of what's inside, let's have a look to the leg module and discrete library. So here there are a lot of references, a little bit around 100 references. And so what we have inside, okay, is the first general information extracted from the datasheet of the manufacturer, but also conduction loss and switching loss data, also extracted from the manufacturer datasheets. And so these loss data are used by PowerForge in different projects in order to compute the losses of the conversion stages. So let's go back to the main page, okay? And now let's consider our first example, the medium voltage drive. So here in this page, we got some general information, okay, of the different participants. For example, here, okay, I shared the project with a colleague of mine as an owner, but he could also be a designer or reviewer. And in this last case, he has just readable rights. So here is the conversion stage we are going to consider. So here are the main specifications of this conversion stage. So here you can see that I have already prepared some different design solutions, okay, benchmarking different multi-level topologies from neutral point clamp topology, T-type topology, flying capacitor topology, and also stack multi-serve topology. So first, we do not consider these three topologies, okay, because they have current distortion, which is not acceptable in the use case we consider here. So just consider to exclude them. And here we've got the full order topology. So to show you how to evaluate a design solution, I'm going to clone the last one. Okay, here we are, and go find it. So here you can recognize here on this system level, okay, the 3 switching cells between the two the different filter, the DC filter and the AC filter, if there is one, the cooling. All these subsystems can be reached with the burger menu, okay, and here we've got the operating point, okay, to set the environment of our power converter. So you can see here a simple OLE model, which models here are mod actually. Okay, so now let's go back to the macro subsystem. Okay, so here you can recognize a T-type topology. So here we've got different variants. So to benchmark different topologies, as I said, neutral point clamp or flying capacitor, for example. But right now, I prefer to show you the benchmark of a power switch. So here we've got a switch from ABB. Okay, and I propose you to consider an equivalent switch, but for example from Hitachi. Okay, here we are. So I'm going to change the name, so it will be much easier to recognize this design comparison space and launch the design. So here we've got some information about the ratio between the switching frequency and the modeling frequency, which is even. So the losses cannot be not very symmetrical between the top and bottom halves. So as you can see, it's quite quick. Sorry. If we have a look at the macro cell, so here you can recognize the waveforms of a multi-level, for example, converter. And as I said, so here we've got the global losses of the power switches, and here we've got the detailed losses. So as I said, because of the even ratio between the switching frequency and the modeling frequency, the losses are not very symmetrical, but as you can see, conduction losses and conduction losses of 473 watts and switching losses of more than 1000 kilowatts. And on this side, yeah, it's a little bit lower, but it's not symmetrical, but it's quite close actually. So as the design evaluation, as you can see, is quite fast. Okay, the designer has the ability to try a lot of solutions, benchmarking topologies on different switches, and then in the first page, the comparison page here, he's able to compare all these solutions. So here you can see 2 graphs on my screen, efficiency versus specific power, efficiency versus power density, and also efficiency versus cost. Okay, and you can see the different designs we have been evaluated. These are these 4. So these are the 3-level topologies. So this is the NPC, this is the T-type, and this is D-type. Okay, this is the last design we have performed with the Hitachi power switches. So it seems that here in this case, the power switch from Hitachi seems to offer better performances in this case. And here we've got the older design solutions with the 4-level flying capacitor, and here the 5-level stack multi-sode converter, which seem to offer good trade-off in terms of efficiency versus specific power. So if we have a look at the efficiency versus cost here, so we can recognize here the 3-level topologies, with the NPC, T-type, and the T-type in a range of with the Hitachi. And here we've got the 5-level, stack multi-sode, and here the 4-level, flying capacitor. So in this case, this design, are much cheaper, because they use lower voltage rating power switches, which are usually much cheaper. That's why the global cost of the converter is cheaper here. So this is the kind, of this is the kind of trade-off. This is the kind of design workflow that the designer can do with PowerForge, and so afterwards, when the designer has made some choice, he can export these design solutions into PSIM in order to keep on the design process. So for example, let's consider that the designer has chosen this 4-level flying capacitor topology. So here we are. So here the first thing that designer has to do is to export PSIM files as a zip file on his desktop in his directory, and then to export into to export into to PSIM and to use it. And now I'm going to give the floor and the handle to Albert, and he's going to show you an example of use with PSIM. Okay, here we are. Okay, Albert, that's your turn.
Perfect, thank you. Let me just see that you're looking at the right screen here. And let me pull over PSIM. Okay, so here's the circuit that has been exported from PowerForge, and it's actually quite a large number of files that come over. These are all described inside of subcircuits, so we can, there's nothing in that one, but, and here's the actual switch setup that has been exported. So all of this comes from PowerForge. You don't need to put any of this together. You just simply need to open the main circuit file in PSIM. Everything is driven from a parameter file, which we see up here, and essentially you can just run the simulation, and we can look at some of the waveforms that happens. So while this is running as well, we're going to look at the voltage, the line-to-line voltage here, and also the current into the motor. And then these devices are also thermal devices, so we'll be able to also track the switching and conduction losses from these and see what's going on there as well. It's just a few more seconds for this to finish. So this is a relatively long simulation, so 300 milliseconds of simulation time. We're only going to keep the last 50 milliseconds, so you'll see these populate up when we get to the last 50 milliseconds. And there is the line-to-line voltage and the current on the motor. So this is what we're looking at here. So P losses just under 22 kilowatts. And then the temperatures on the devices are the bottom ones here. And then the middle line here is showing us the current on the motor, and we can also see the voltage on the top side here as well from the line-to-line voltage. We can pick up, or I could do it actually this way. So I can pick up between the cursors here, and we can start doing, whoops, redraw. Pick up between the cursors here. Well, maybe let's grab an in-phase period of the current, and we'll do a THD measurement there as well. So let's come down here and we'll do a THD. Base frequency is it's 50 hertz, I believe, and we can see what our THD looks like. All this is, I'm not sure. I'm using a version 12 version, and I'm not sure if that is actually giving me the right number. This is a beta version. Sorry. What else can we look at? And essentially, we're able to analyze through, and then if we wanted to just pull up we can delete these screens, or we can pull up a new window here, and we'll just look at the UAB. And we can run an FFT of this as well if we're inclined to do those sorts of things. So there's lots of different analysis things that we can do inside of PSIM. and that allows us to really kind of dive into how this is working. Now, the other fun thing that we can play with here is the script that I've written on this subject so far. So if we come into the scripting tool, we can open up a script, and what the script is that I've written is we're able to, I'm basically just taking the same parameter set from the parameter file and declare, so these are all the parameters that PowerForge exports in order to define the circuit. And then I'm declaring an array here of different frequencies to run through, so 30, 40, 50, 60 hertz. And then I'm able to, let me just change that to simulate, and I'm going to run this script right away because it does take a moment to run. And we're going to generate all of these files over again. So we're going to get a simulation that's going to be the baseline simulation, what we just got. Then we're going to get 4 simulations here, 1, 2, 3, 4, that cover different the operating frequencies. And then we're also looking at changing, then we combine those to look at the currents and power losses. And then we also have 2 where we're changing the equivalent circuit model, increasing the resistance by 20%. And then we also have 1 where we're increasing the DC bus voltage by 20%. You know, these scenarios maybe are not the most well developed, but the idea here is to kind of show that this is possible. So I am just going to go ahead and delete these, and these should all pop up when we're done. So we'll just run the script, and while it's running, we'll talk about what's happening. So the first step here, this is our baseline simulation, and I'll just put in some comments here. So run baseline. And the first thing that's happening here is we're running to 250 milliseconds. So the first simulation is running this to 250 milliseconds. And then what happens, we can see we've got a time step declared here, which is the switching speed of this is 600 hertz. And we can look to see what that evaluates as right here. So that's time step of 3 seconds is what we're actually going to run with. So that's 200 points per switching cycle. And although maybe that's, so then what's going to happen is we've run the baseline simulation, and then we're going to branch and change the time step and go dramatically smaller. So 2 microseconds is what we're running with now, and we're just going to run the last 50 milliseconds sort of over and over again. And so this is how we get the baseline simulation here. So you can see the difference here is that we're using the asimulate call versus simulate. So simulate runs and we wait for this to return. When we use asimulate, it's going to run them on the next available core. So now what I'm doing is I'm multi-threading the next set of simulations. And all I'm doing is using this load flag. So starting from that 250 millisecond point and running 3 different simulations where I'm changing the I'm changing nothing, and then I'm changing the DC bus by 20%, adding 20% to it, and then I'm changing the equivalent resistance, changing that, and changing the DC bus back to what it was, and then I'm running those. So these 3 simulations kind of run, and then while those are going, I also then set up another set of simulations inside of a loop here, and these are changing the frequency by these predefined frequency amounts. So I'm using this array, and I'm going to run 30, 40, 50, 60 hertz, and I'm going to run them inside of a loop. So then I'm just changing that parameter, rerunning, and while those are going, then I'm compiling the results, so the losses and the currents into combined waveforms, and then I'm going to output those. So hopefully, oh, here we go. It's finished. That was perfect timing. Whoops. So here are the results. Accidentally closed it. Open that back up again. Let's just pull them all over. Okay, so there are the, we'll just look at the motor on that one. So that's the base value. This is the frequency at 30, frequency at 40. I'll just add them all on. At 60, and then these are all of the, you can see the combined motor losses there. So those are all of them, and they're all starting at the same point. So we're giving it some time to hit steady state. These are all of the power losses in combined plot, and then the I motor of the various ones. So all of these got automated for us. So this is with the increased DC bus voltage. This is with the different, this is the increased resistance, and here's the power losses. So I don't want to spend too much time playing around with all these simulations, but the basic idea here is that we were able to schedule all of these simulations. That script ran, and while it was executing, we made efficient use of our processor by running 3 of them kind of asynchronous, like on available CPUs, and then we also then ran some of them from a loop and extracted information and combined the graphs together for informational purposes. I hope that's clear. Guillaume, is there anything I missed there?
Yeah, that's very clear.
Okay, perfect. Is there any other questions from the attendees before we move along and I pass back to PowerForge?
I think we do have a question, but it's for the PowerForge path.
Perfect. Okay, well then, why don't I'll pass you presentation back. I will change presenter back to you, and
Okay.
I'll let you continue along.
Yeah, so the creation, okay, is the creation as from Timothy. So this can we mix the different techno IGBT and silicon carbide, for example, on the same design? So the idea is that okay, you can compare different technologies in one design and on one other design. And as PowerForge relies on homogeneous switching cells, it is not possible to combine different technologies, as we don't have these data from the manufacturers. So for example, if I consider the example of the of the medium voltage drive with the MPC, for example. Okay, let's have a look to the macro cell. Okay, so here we've got the first switching cell and then the 2 other switching cells. So here, in order to compute properly the switching losses of the switching cells, here the switches have to be the same because we rely on data from the manufacturer. But if you want to create your own module, your own NPC module, or your own leg modules, it is possible, and thus you can add your own data. So I didn't present this feature, but I'm doing to do it right now. So for example, here, if there is a reference, okay, which is not in the database, okay, the user has 2 options. So first, request a public reference, okay, so that the power design technology team will handle the process. And so that's all. But if you want to create your own leg module or your own NPC module, because you are making a custom module, or because you want to mix different technologies, for example, on your own, you can do it by creating a private reference. Okay, so here these are just general information from the datasheet, and then here you just upload, okay, 2 different files, 1 file for the transistor, 1 file for the diode. And here we right now, okay, we consider a format which is an XML file from Plex, because a lot of manufacturers already provide, okay, their switching and conduction loss data using the Plex format. So so that's the possibility to mix different technologies. Okay, so I hope it answers your question, Timothy. And now, if you agree, we can keep on with the next example, which is a DC fast charger application for electrical vehicle. So here, this is the example we're going to consider with a central inverter, okay, from the network, and a battery energy storage system. And then several DC terminals in order to be able to charge different vehicles. So here I propose you to consider one of these terminals with the following requirements: a high voltage of 700 volts, a power of 50 kilowatts, and a low voltage of 450 volts. So, and we are going to apply the workflow first using PowerForge by benchmarking different power switches, but especially the switching frequency, and see the influence of on the efficiency versus the specific power, but also mass and loss breakdowns. And then after the PSIM export, Albert will show you how to close the control loop and an example of a code generation for an MCU implementation. Okay, so let's go back to PowerForge. So now I'm going through the second example. So this is the conversion stage for the DC fast charger. So here you can see the design I've already evaluated. So this is classical topology, a two-level here using a classical power switch with silicon IGBT, and here this is another family with the use of silicon carbide MOSFETs. So here, for example, I'm going to show you, okay, the influence of the switching frequency. So you can recognize, okay, the schematic of the power converter. Okay, so here, this is the schematic of the two-level topologies using this power switch. Okay, and so here we can change the parameter of the switching. For example, let's consider a switching frequency of 25 kilohertz. So once again, I'm going to change the name so it's easier for the comparison. Let's evaluate design. Okay. So as it's a DC-DC converter, it's a little bit faster than for the medium voltage drive application. So yeah, so here we've got the general waveforms of the power converter. It's quite simple because it's just a two-level DC-DC converter, and with the different power switches, loss. Sorry. And so now if we go back to the comparison page, okay, to have a look at the different graphs. So this is once again the efficiency versus specific power, and here the efficiency versus power density. So this is the first family with classical silicon IGBT, and this is the second family with a silicon carbide, okay, MOSFET, which obviously offers here better performances. But what is interesting here is that I increased the switching frequency from 2 kilohertz, okay, to 16 kilohertz, and here there is clearly a kind of optimum around kilohertz. In terms of efficiency versus specific power. Indeed, here, when I increase the switching frequency, okay, I increase the specific power. So here, it can seem obvious, of course, because as I increased the switching frequency, the filter mass and filter volume have probably decreased. But what is a little bit surprising that as I also increased the efficiency, whereas as everybody knows, usually the power switch loss increase with the increase of the efficiency. So For example, to explain this phenomena, let's compare two different designs. For example, the 2-level with the 6-level. Okay, and so now we can have the different breakdowns of mass, volume, and also loss. So as I told you, so this is the design at the switching frequency of 2 kilohertz, and this is the design at 6 kilohertz. And as you can see, the global mass of the power converter has decreased, and especially due to the decrease of the low voltage filter. But as you can see here, the global losses have also decreased, which explains why the efficiency has increased. Why? So as you can see in green, these are the losses in the power switch. So these losses have increased from 2 kilohertz but to 6 kilohertz. But this increase of losses is compensated by the decrease of loss in the filter, and especially in the inductor of the filter, because here the inductor is smaller, so we have lower DC losses. So that's why here the efficiency has increased. But of course, this phenomena has an end. And for example, at 16 kilohertz, this is not the case, or 20 kilohertz, for example. So it's I add this third design solution to compare this, and we have a look at the loss breakdown. So this is the loss breakdown for the last design. So as you can see, from this design to this design, we have still decreased, the losses in the low voltage filter and in the inductor. But this is not enough to compensate the increase of losses in the power switches. So that's why here the efficiency is decreasing. So this is typically the kind of benchmarking for the switching frequency we can do using PowerForge in order to have the designer to choose the right frequency of his design, and also to choose the right device. So for example, here Albert will keep on by showing you an example of this design, which is the 2-level using a silicon carbide. So just for example, as I showed you with the medium voltage drive example, just download the zip file and to import it into PSIM. And now once again, I'm going to give the floor to Albert. And it will show you an example on how to close the control for this fast charger, and an example of code generation for MCU. Albert, you have the floor.
Okay. So again, here is the export unpacked from PowerForge. There's a couple extra files in here which I have made. These are going through the closed loop a bit, but essentially this is what you get, and this is what you get out once you open it up. I have added in some intermediate steps here as I've closed the loop. So let me just kind of like highlight what is new. So the export is open loop, and I've added in, because we're going to do digital control, I've added in these digital control elements here, these sampling rates and these order holds, and I've replaced the stock reference with my own reference, which is this right here, which I'm going to use to close the loop, do average current control on the inductor current, which is the current flowing. So here's the filter. It's the current flowing in this branch right here. That's the code generation one. And then let's just disable this. Okay, so the way so we could have done an AC sweep on the on that multi-level inverter. When we do a frequency sweep in PSIM, we are completely agnostic to the switching topology that you're using. All we care about is that we're injecting a frequency, and then we assign somewhere for that that perturbation and gain change to be sensed. So let me just run the simulation. So what we're doing here is also in the and it just crashed. Okay, this version of 12 I didn't realize was this unstable. It was working fine for me earlier. I won't run the sweeps then. I will just, thankfully I have the simulation files popped up. Okay, so this is what the current feedback looks like. The current control open loop looks back. So the red line is the, and let's just remove the voltage for now. So here's the two current. This is the current. So here's the amplitude and here's the phase. And we can see we're rolling over the phase over here, and we're doing digital control so that the impact of that 1/z delay is being seen here. So we can import this into a design tool called Smart Control, which we provide, which allows us to tune that controller quite easily. So this allows us, basically we choose an operating point in here, and as we move this operating point around, we can see the change of the step response, and this pink line here are going to be our control to output transfer function. So let me just turn off that. So this is where we're going to look to see what our phase and gain our crossover frequency and our phase margin is, and also make sure we've got enough DC bus to hit steady state, quick DC gain, and we just move around, and this generates some PI. This is doing a PI for us. There's lots of other tutorial videos that cover this kind of thing in detail, but I will skip over that for now, and we'll come back to here. And this is then, I did the sweep to the current loop. I did a sweep to do a voltage loop, and we end up with this setup here for a closed loop simulation, and we end up with waveforms that look like like this and there's no data. That's annoying. Sorry, my beta version is not behaving right now. I wasn't expecting that. And then we've also then run over to the closed loop form with cogeneration. So this is the real fun trick here. So now what I've done is I've digitized that simulation. So here where we have the PWM, the controller, I've come and wrapped that in PWM target files for the F28335. So this F28335 output block here, we're defining the switching speed and the dead time. Over here, we're doing an ADC sampling setup, and then I've also set it up so that there's some logic in here, so I can run it with just open loop to start with, and then I can also set it up so that we close the voltage loop. We run in constant current, and then I close the voltage loop once we hit a specified value. Let's see if this one will want to simulate. So this one should be simulating, right? Okay, so this one does simulate, but what we should do here is generate the code. So this is the .c file that we generate, and there's lots of tutorial videos that cover how this code is basically to bring it over into CodeComposer Studio. So this is the .c file as it was imported, so we can see the timestamp here, June 26, June 26, and it's basically a one-to-one with a schematic. So we end up with interrupt routines declared based on the sampling rates that are seen in here, and we see there's basically a one-to-one. So each block ends up with a variable over here, and then this gets. We don't have a lot of time, so I'm not gonna spend a lot of time showing the import process, but I will turn on my webcam and you will get to see the setup, because we will actually use this code. And we wanna show this side and down. So here's the processor. This is the F28335. And I've already loaded it with the code. I've loaded it into Flash so I can just turn it on and it will run. and this is a Typhoon Hill simulator. So I've built a real-time simulation. So I've built a real-time simulation of this in the hill system, and then we can run it all. So this is the, let me just close some windows down. Okay, so here's the hill equivalent circuit. So we've basically just a simple buck converter. I don't have a synchronous buck, so I'm not allowed to implement the same switch in the way the hill system simulates it. So it's just an active switch and a diode, as opposed to if we look back here, it's the two active switches. So the synchronous rectification, again with the thermal devices under the hood. So, and then I load this onto the hill system, and then we've got a control panel which I can run this on. So what I'm going to do first though is let's just look at the system in open loop. So I can connect to the processor while it's in operation by going to our DSP oscilloscope tool. So now over this cable here, I'm going to connect to the processor over serial communication. And what I'm going to be able to do is control, if you see in the schematic here, I've set up points where I can control things. So I'm going to be able to toggle this between open loop and closed loop. And I'm going to be able to monitor some waveforms as well. So let's just put this into open loop. And let's just define a straight 50% duty cycle. So what we can look at is we should see PWMs right now. So this is a little oscilloscope is what you're looking at, and we should see 50% duty cycle. And then I can also, on the fly, change that, say, let's go to 10%. So there's 10%, and there's 90%. So I'm able to control this. So this whole thing is working in real time. So what I'll do now is I'll start the hill. So the hill hasn't been doing anything right now. All we're doing is just running this in open loop. And I changed basically in the PSIM simulation, what I'm doing is I'm toggling this mux over here and just defining the input to the PWM. So here's my open loop close flag, and here's my open loop ref. So I'm just changing those values to change what's going on. Okay, so let's move those out of the way, and let's bring back the hill. Okay, so now what I can do is actually start the hill simulation. And so we were in that open loop scenario, and let's just put it onto the scope. So this is the system running in open loop now, and we can see that there's not that much current. We're going to need to get up to 110 amps, and I can still just fool around with this a little. So there's 20%, and you can see I'm able to, this is the current here, and this is the current in the inductor here, and there's the voltage on the battery here. And I'm able to change this duty cycle, and we can see how that impacts these waveforms up here. So let's make that a little easier here. So we can see what these look like. So there's the sawtooth on that. And then if I, what I'll do is I change the size of the battery. So I'm just going to make the battery discharge by dropping the DC bus voltage. So we should see the battery discharge. And then what I will do is I will simply, I'll put it back into closed loop. And then we should see, I'll put this to a capture mode, and we should be able to see the battery charge in constant current, and then switch to constant voltage. So we'll go to capture mode now, and I will change this DC bus back up to 700 volts. And loop update all. Okay, so that, okay, so that's running, and then we'll go back to closed loop update, and then we will force the trigger, and we should if I did things properly, we should see, so this should be charging at, okay, so here's the current. So I'm monitoring the current from the analog input, and we can see that we are progressing into, so there's the current is discharging or slowly going down as we go into the constant voltage change. And we should, this is waiting for 50 seconds to pull data, so we just need to wait just a few more seconds, and it should be ready. Any questions while this is running, while we're just waiting for the capture to finish?
Yeah.
Almost done. There we go. So we can see constant current at the design current was 110 amps. These were real-time waveforms that we captured. The voltage of the battery went up to 420 volts, where I switched over to constant voltage charge, and then we can see the current slowly changing as the battery charges up. Again, so all this was real time. And the advantage of running this in real time is I don't have to set up a power supply with the hill simulations. I don't have to set up a power supply that's rated at 50 kilowatts and risk blowing it up just to make sure that my control loops are working properly. So that's the advantage of this system here. And then all the code was generated from PSIM, and I didn't have to change a single line of C code in order for that to work. And again, there's lots of videos on our tutorial webpage that go with that in a little bit more detail. And if there aren't any questions, I'll pass the presentation back to Guillaume.
Yeah, sounds good. I like this this illustration, you know, of the whole process from our PSIM file, which has been directly extracted from PowerForge. Okay, to this example of how to close the control loop. And then to the code generation and to a real-time simulation. So this shows how the designer can cope with the whole process of a power converter design to the prototyping using this complementarity between PowerForge, PSIM, and also Typhoon Hill. So yeah, I think it's time to jump to a conclusion. So first of all, yeah, to go back to the workflow. Okay, we have illustrated with two examples. So first, we have shown that the user has the ability to benchmark different topologies, including multi-level topologies, but also power switch reference and switching frequencies. So using PowerForge in order to compare different solutions and to choose the ones which match his requirements, and then to export this solution in PSIM. And then maybe Albert, you can summarize for your thoughts.
Yeah, essentially, you know, PSIM is a general purpose simulator specifically made for power electronics. So you can generate waveforms, check losses, check operating conditions, make sure that your transient temperatures on the devices don't overshoot. You can close the loops, you can generate code, you can you know, you can add in nonlinearities into the system, you can control an actual motor, you can do all sorts of things. I mean, a general purpose simulation tool is very important for this sort of application.
Yeah. Okay, so that was the conclusion for the workflow of the power electronics engineer using both PowerForge and PSIM. So now I think that we've got a little bit of time. If you have some questions about this combined use of PowerForge and PSIM. Okay.
I have a question for you.
Sure.
The mass that you consider, so you do the power density or the specific power. What makes that mass up? Is that the switches, the heatsink? Are there any other of the passive components that are being considered as well?
Yeah, thanks Albert for asking this question. For example, with yeah, let's have an example. So we'll have the picture. Okay, so the mass is the sum of all the discrete elements. So for example, with this slide design, okay, here. We've got a global view of all the elements. Let's say here in blue the capacitors, in black the power switches, here the cooling device, the inductor, and once again the capacitor of the low voltage filter. So here the mass of okay, the design which has been evaluated is just the sum of all these masses, such as for the volume and the loss and the cost breakdown.
Okay.
Okay. Let me know if you have more questions.
How many levels can you consider in your so far? Like a flying capacitor topology? How many levels can you go up to?
Well, with the flying capacitor, there is no theoretical limits. For example, here, so this is okay. Also, this is the DC-DC fast charger, so I can consider a flying capacitor. So, for example, let's clone this design. Okay, let's switch to a flying capacitor macrocell. So here, the designer can set up himself. Okay, the number of switching cells. Okay, to consider in this macrocell. So here, the number of levels in this topology, for example, is just the number of switching cells plus one. So in this case, we've got a 3-level, okay, flying capacitor. So here, I know if we consider 6 switching cells, we'll have a 7-level flying capacitor. Yep, switching cell.
Okay.
So yeah, thank you.
Okay, well, it doesn't look like there's many other questions, so maybe we should wrap.
Yeah. Okay. Well, maybe we can end if we don't have more questions.
Yeah, I think that's it.
So, well, thanks a lot. Aurelie, do you want to conclude, or?
I think it's pretty self-explanatory. You know, to be able to efficiently consider topologies for more than just based on efficiency, mass, cost, is something you cannot do with just a simple simulation tool. So these tools on the front end that allow you to come up with a topology and consider them quickly before progressing with your design, I think is a very powerful thing.
Yeah, thanks a lot. And it's yeah, this is the purpose of of an early stage design phase tool, and that's why PSIM is also a very interesting tool, because it's complementary. It can do things that a design tool such as PowerForge cannot do. So I think that here we illustrate a good complementarity between two different tools for the power electronics engineer.
Yeah.
Okay, so do not hesitate to contact us. If you want some more information, you can follow both of us on our website, on LinkedIn or Twitter. Okay, so thanks a lot for your attention. Thanks a lot for all this work, Albert. And I will see you soon for next webinar maybe. With Basim.
Thank you so much, everyone. Thank you, Graham, for all the work you've done with PowerForge, and a very interesting tool. And I think, yeah, excited to continue presenting the tool, the solution workflow.
Okay.
Thank you.
Yeah. Thanks a lot.
Okay.
Bye-bye.